Okay, so we're in the last topic of chapter 8. So this is effectively, again, a electromagnet lifting a car up. And who's doing the work? Well, we know the rough answer to that, but we'll just do it as a problem. It's a dynamical problem. And in this example, so he works it out in some detail, but there are parts of it that have been assigned to homework. So what I thought I'll do is I'll sort of reconstruct and hopefully make the discussion clear and do parts of the problems that he takes for granted. So to do that, so that we don't stumble across the difficulty in the middle of the problem, let's solve all the prerequisites ahead of time. So so technically, what I'm trying to do is problem 812. And this has a larger purpose, of course. So problem 812. Okay. So we have two loops. These loops are not moving. And this one has a current IA, and this one could be in any direction, IB. So everything related to this one, I'll call it B, and everything related to this object, I'll call A. Okay? And so I'm going to compute phi B. What does that mean? It's the magnetic flux on circuit B. These circuits are rigid. They're not moving. They're held in place. The currents are, of course, free to change. So it suffers a magnetic flux due to two things: mutual inductance and self-inductance. For self-inductance, so let me write the mutual inductance term just because I have that here. By definition, it is that. And then, of course, self-inductance. Oh, it's B. I wrote B first, LB, I, B. Similarly, I have A, B, IB plus LA, A. So because of that, there's going to be an induced EMF here, which is and so this induced EMF is going to counter the flux. Yeah? So as a result, the charges have to move against the induced EMF. So there's work done by the induced EMF. So it's easier. So if I were to say, what's the notation I use? If I were to say W, I can do two things, and then I won't know how to go forward. So don't write this down. First of all, I have to fight the induced EMF. So I have to do and B, because I know what these two guys are. And also, then I have to do, this is EMF, so that's work done per unit charge. So then I need to do unit charge. I don't know what's the charge in there. I just know what's the current in there. So what I could do, make it a current. Yeah? And so then it becomes what is that? IB minus, oops. So let me plug that in. These two negative signs go away. And so I get EB, which is d dt of phi B. Let me put this in. Now, mutual inductance is the same. So I don't need to put BA and AB. I just call them M. So I have M IA plus, what am I? Yeah, LB IB times IB plus DDT of M IB plus LA IA times IA. Yeah? So again, these things are not moving, so and then I'm going to multiply IB plus LB DDT of IB times IB. So these derivatives are sure I'm doing it correct, plus LA. Yeah? So I can combine these two. They look like product rule, so I can write this as yeah, plus where did this come from? If I take the derivative, I get 2, which cancels this, IA times the derivative of IA. And that's that. Yeah? So what I want is not really ddt. I bring out the ddt all together, and I get 1/2 LA IA squared plus 1/2 LA IB squared plus M IA IB. So I want to clarify the language that I've used in this. So what I'm doing is I'm looking for, we had something like this. This is the work done, rate of doing work by the back EMF. Correct? Correct. And then you get the expression that we need. dW equal to d. I'm just going to get rid of the time derivative. And 1/2 LB IB squared plus M IA IB. Getting rid of the differential, calling this the stored potential energy in the system. I can get rid of the D. And so we had a similar expression. So this is the rate of work, doing work against the back EMF. Yeah? And from that, we get the energy stored as potential energy, because it's a change in the potential energy that causes this work done. We had just this term, 1/2 Li squared. Now we're just doing it. If there are two terms, well, it comes from individual Li squareds and the mutual inductance. The note here we have, they're both IA, so we put a 1/2 in taking the square root. I mean, in taking the derivative. Here, the two currents are different, so we don't have that 1/2 term. So energy stored in the field is this combination right here. If we're able to maintain the current, then that's the energy. Otherwise, something has to do work against the back EMF. So we need this fact for the problem today. The other fact that we need, I believe, was an example problem. I'm taking a little circuitous step because these are important points, so I want to clarify. In fact, here I don't particularly agree. I'm not too happy with Griffith's notation of a sign, and I'll tell you what I mean. But all the physics is absolutely correct, and it's just a matter of preference. But I want to state one more result that I would like for you to remember. I can present that as we come, as we go along. So where am I in the book? I'm in the last section. Magnetic forces do no work. So that's what I'm working on. I want to clarify many things. One, for example, is if you have a XY plane, so be it a cylindrical coordinate system or a polar coordinate system, and you locate any point, this is the angle phi, and this is my vector phi hat. Okay, so phi hat is going to be.
Is that a function or a circle? Part of a circle?
It's a part of a circle. Okay, so phi hat is going to be cosine of, look, phi plus 90 degrees in the x hat direction plus sine. It's always cosine and sine. The question is, what's the angle? It is phi plus pi over 2 in the y hat direction. Okay, well, this is minus sine phi x hat plus cosine phi y hat. Again, you've known this all along. Now suppose I have a loop and I am integrating along this loop what should I get? If you integrate along the loop, it's the final point minus the initial point. But if it's a closed loop, it's the same, right? I should get 0. So we should be very careful. I would want to write initially, say this is radius A. Then this is A times d phi hat. So again, don't write this down. If you say, well, that's equal to phi hat, and this is my integral A d phi, this is wrong. You will get 2 pi A phi hat. That's not true, because phi hat is a function of the angle as well. So obviously, A times minus sine phi x hat plus cosine phi y hat d phi. Now, I can bring the x hats outside. Why is that? It doesn't depend on? It doesn't depend on? Yeah, if you integrate sine and phi from 0 to 2 pi, you're going to get 0. The reason I wanted to mention that, this is all sort of prerequisite for what we're going to study. If we had the magnetic force is, on a loop, is IDL cross, it's in general, it is IDL cross B. And the integral is to be done here, right? But if B is uniform, then there's no net force on a loop, because let's say bring even this out. We just mentioned the beginning point is the same as the end point. This is 0. We've talked about this plenty of times. Just all, just good old-fashioned recall. So if B is uniform, there's no net force. Okay. Now let's state the problem at hand. Suppose, so magnetic forces do no work, right? That's the section. So suppose you have a magnet an electromagnet. Something is causing this magnetism. And here's a car. What we will do is we'll model the car as a loop. Yeah? I want it to be a very, very, very small loop, but if I draw a small diagram, you won't see anything. So let me make it slightly bigger. And the loop should have a current in it. It could be an induced current, no problem. Iron is, metal is ferromagnetic, so you can induce a current in it. And the way we will induce a current in it, just to be very specific in our calculations, we'll affix a charge, just so that we can calculate things. We'll say that there's a charge density of lambda. And this charge, this loop, is spinning around with some omega, some angular velocity.
So the I is the result of the omega?
Correct. So then I is charge times the velocity. We're only concerned about magnitude, so charge times velocity. V equals R omega. R in this case is A. That is the current in the circuit. Now let's look at the magnetic field. The magnetic field will look like this. The lower end of a dipole, if you will. So the magnetic field has two components. So I'm going to take this and just draw it here so you can see the exaggerated effect, okay? This magnetic field over here will have two components. This is the S component of the magnetic field. Mind you, this is cylindrical coordinates, so pointing inward, and this is BZ. Correct? So if you draw a circle here, you will see why the S component. And you also note that BS is less than 0. It's pointing inward. In Griffith's calculation, he just picked BS to record the magnitude, so it is a positive quantity. We won't do it that way. We'll just clarify it so that I think the argument, at least to me, it sounded a little better. Okay, so let's look at the magnetic force on this loop. We have done all the hard work to compute the loop. We talked about when it goes to 0 and whatnot. So it is I dl, A times d phi, in the phi hat direction, cross B. B is some bz in the z hat direction, plus bs in the s hat direction. Z phi hat cross z hat is what? Phi hat, this is s hat. And hopefully, when you do this, if it is in the exact center, it's going to cancel itself out. Because if you go through the loop, it's s hat just pointing everywhere outward, and the net force will be 0 if things are uniform. If it is not uniform, it's the car moving right or left so that it centers itself. So we're not really interested in that. We're only interested in the upward force. So let's just perfectly align it so that this term cancels. And so then you get F is equal to integral, all of these things are constant, but it's a loop. I have a BS phi hat cross S hat. Negative C hat. So I get negative, and the way Griffiths writes it, lambda for I, A times A is A squared, omega, d phi is going to give me a 2 pi bs z hat. Let me make sure the number is correct. 2 pi a squared omega lambda bs. Yep, z hat. Now look, this is a negative. This is a negative number. Car is being lifted. Now, the work done, scalar, it's f dot dz, z hat pointing that way. Z hat and z hat is 1. So I would get minus, let me clean this out nicely, 2 pi lambda a squared omega bs dz. Yeah, that's the expression we'll need. We'll need to hang on to this for a while. So somebody's doing work lifting the car. Okay. Now, he writes an expression that I'm not too fond of. I want to clarify where that expression came. It is correct. It is easy to write. We have seen it before. But let's do this in detail. Hang on to this in your memory. Eventually I'll erase it when I get to that part. We've had a similar argument before. But it's one of those arguments that you have to revisit a couple of times before it sinks in your head. So let me at least do it for a second time. So imagine your rig, or your car. Yeah? The car is lifted. So this is at some time t, this is at some time t plus delta t. And then, as usual, Griffiths calls this the ribbon. So that's the shape created by the loop of the car. Okay. I'm going to pick a direction I want to compute flux in. It makes sense to compute flux in this direction. So I'm going to call this N2, and I'm going to call this N1. The change in flux in the loop should do delta because I'm going to integrate, is B at t plus delta t. In our case, B, the magnet of the car. This is the magnetic field produced by the electromagnet. It is not really time dependent, but I'm just going to leave it there for a while. Dot N2 dA minus B T dot N1 dA. So when I say N2, I mean along this area. When I say N1 over here, I mean along this area. This is the change in flux on the car, modeled as a loop. This is the magnetic field produced by the electromagnet.
So I would assume N1 and N2 don't change in almost.
No, not if it's going
Yeah.
perfectly perpendicular, no. I'm just writing them as N2 and N1 to locate the surface.
Yeah.
Yeah.
And what would be the only thing? Would the only thing that changes the B?
Even the B doesn't change in, well, it doesn't change in time, but it can change in intensity.
Yeah, as a function.
Yeah. Not because it's directly a function of time, but it is located closer to the magnet. Okay? So then what I'm going to do is at t equals, no, at t plus delta t, since divergence of B equals 0, I'm going to get B, all t is going to be evaluated at t plus delta t. T plus delta t. This statement is going to be independent of this. This is always true because and R is the normal of the ribbon. Again, in this case, it's easy. It is S hat. But this argument is general. I'm doing this to get the magnetic flux. This is simply divergence of B integrated over a volume. Yeah? Oh, sorry. Everything is at T plus delta T, huh? Because I'm evaluating this over a volume at that time. So what I'm going to do is rewrite this expression, and you tell me where it came from. I got rid of this 2 integral, and I brought it to this one at a different time by solving for this. This is equal to, I put equal to here and cancel the minus here and put a minus here. Did the algebra work out? Chip, look, stare. I solve for this in terms of this and this. And I use this expression over here. Yeah? Again, your Griffiths doesn't have a negative sign here. The origin is the same origin. Huh? Now, look at this. This is along the same surface. Is B time dependent? B is produced by the electromagnet, right? It's not time dependent. So this term goes to, and the explanation for that is the electromagnet is not time dependent. It is on the same surface. Yeah. Of course, if you go up to the higher surface, it changes. Yeah. But this is on N1. And so this is B of T plus delta T. We know the normal direction, it's S hat. It really shouldn't matter. And times the area of this guy, the cylinder. It is 2 pi A dz. Yeah? I'm going to write this as dz dt dt. It shouldn't bother you. Let me write it as I can afford to do this one more time. This is dot s hat 2 pi a dz. I can, because z is a function of time. The height of the ring is a function of time. So I can change it to, I'll tell you why I'm changing it. Because I'm not really interested in flux. I'm interested in rate of change of flux. That is the induced momentum. So two things. So then d phi dt, the integral simply goes away. Yeah? And we want only one order of term in delta t. This already has a delta t. So do we care about this delta t anymore? No. So this is minus b dot s hat is and so the EMF induced on the car is equal to minus d phi dt, so that is bs 2 pi a dz dt, which is less than 0. So let me now make sure you follow this.
Because BS is less than 0.
BS is less than 0. So let me draw now the car itself. So here's my car. Yeah? And the EMF is produced the other way, against the current. Again, Griffiths might have a negative sign here because for him BS is the absolute value. Okay, this is the induced EMF. EMF is equal to force per unit charge dot dl that is equal to dl is in the phi direction, so f of l, again a times d phi. It's a scalar. I don't have any more things. So this is nothing but 2 pi a f of phi. I have two expressions for EMF. And therefore, I set this equal to that, and I get f of phi equals bz dz dt. Again, this is less than 0. Or as a vector, the force per unit charge is bs dz dt. So this EMF is creating an literally now the term, is creating an electromotive force in the car. And it is designed to go in the opposite direction of the current or opposite direction of the rotation. What does this force do? Creates a negative torque. See, we're trying to blame the work done. Yeah? What we're going to show is the rotation of the loop decreases, thereby losing its rotational energy. and going up. Conversely, maybe we can say, if you maintain the current, there's the battery doing work to maintain the current, and that is what is lifting magnet up. Anything but the magnetic field. We'll spend more time on this to get to that conclusion. Yeah? Okay, this creates a negative torque. Torque N is R cross dF. In our case, this is also a closed integral. So this is equal to R. That is nothing but A times S hat cross, it's this force, but this is force per unit charge. So let me write times the total charge. So let me first write BS dz dt. This is the force per unit charge. What is the total charge? Lambda times 2 pi a. I wrote it as an integral, so let me just write it as lambda times a times d phi. I mean, total charge is, the magnitude is constant, so there's no integration to be done. But I wrote it as an integral, so I'm writing it as d phi, that's all. And so a few things. S hat cross phi hat is what? Z hat. This is BZ dz dt, A times A squared. There's a lambda, and d phi is 2 pi Z hat. But this is a negative Z hat. That means if the car is modeled as rotating this way, it creates a counterclock torque. So this is a counterclockwise torque. What's the work done by torque? It is work done by force is F dot dx. Work done by torque is N dot d phi. Angular. So I think I'll have a good second lecture on this. So work done by this is N d phi in magnitude. With work is it's magnitude. So that can be written as N times omega times dt. We have the expression for N. It's right here. Bs dz dt a squared lambda 2 pi, then omega from here, and then dt. The dt's cancel, and I get a squared lambda 2 pi omega. You recall this expression? It is precisely the work that was done in lifting the car. So what we have learned is, as the electromagnet attracts the car, there's an induced EMF in the car that creates a negative torque, equivalent to a negative torque. This torque reduces the rotational energy of the car, modeled as a loop, mind you. And in doing so, the work done by the torque is precisely the work done in lifting the car up. So there is some amount of balance here.
Okay.
How does it look? Any questions? I don't think I can cover what I want to cover. It's a complete story, part 2 of this. So I'll wait till the next time. But before I erase the board, I have time for questions. Is everything clear? It should be, because we went through it in great detail. Okay,
I
good.
do like how this chapter, that we pick 2 different ways of looking